Can we survive technology? John von Neumann. Member, Atomic Energy Commission. Fortune Magazine. 1955. Narrated by Skeptical Waves. The Great Globe itself is in a rapidly maturing crisis, a crisis attributable to the fact that the environment in which technological progress must occur has become both undersized and underorganized. To define the crisis with any accuracy, and to explore possibilities of dealing with it, we must not only look at relevant facts, but also engage in some speculation. The process will illuminate some potential technological developments of the next quarter century. In the first half of this century, the accelerating industrial revolution encountered an absolute limitation not on technological progress as such but on an essential safety factor. This safety factor, which had permitted the industrial revolution to roll on from the mid-18th to the early 20th century, was essentially a matter of geographical and political Lebensraum, an ever broader geographical scope for technological activities, combined with an ever broader political integration of the world. Within this expanding framework, it was possible to accommodate the major tensions created by technological progress. Now this safety mechanism is being sharply inhibited, literally and figuratively. We are running out of room. At long last, we begin to feel the effects of the finite, actual size of the Earth in a critical way. Thus the crisis does not arise from accidental events or human errors. It is inherent in technology's relation to geography on the one hand and to political organization on the other. The crisis was developing visibly in the 1940s, and some phases can be traced back to 1914. In the years between now and 1980, the crisis will probably develop far beyond all earlier patterns. When or how it will end or to what state of affairs it will yield, nobody can say. Dangers present and coming. In all its stages, the Industrial Revolution consisted of making available more and cheaper energy, more and easier controls of human actions and reactions, and more and faster communications. Each development increased the effectiveness of the other two. All three factors increased the speed of performing large-scale operations: industrial, mercantile, political, and migratory. But throughout the development, increased speed did not so much shorten time requirements of processes as extend the areas of the Earth affected by them. The reason is clear. Since most time scales are fixed by human reaction times, habits, and other physiological and psychological factors, the effect of the increased speed of technological processes was to enlarge the size of units, political, organizational, economic, and cultural, affected by technological operations. That is, instead of performing the same operations as before in less time, now larger scale operations were performed in the same time. This important evolution has a natural limit, that of the Earth's actual size. The limit is now being reached, or at least closely approached. Indications of this appeared early and with dramatic force in the military sphere. By 1940, even the larger countries of continental Western Europe were inadequate as military units. Only Russia could sustain a major military reverse without collapsing. Since 1945, improved aeronautics and communications alone might have sufficed to make any geographical unit, including Russia, inadequate in a future war. The advent of nuclear weapons merely climaxes the development. Now the effectiveness of offensive weapons is such as to stultify all plausible defensive timescales. As early as World War I, it was observed that the admiral commanding the battle fleet could lose the British Empire in one afternoon. Yet navies of that epoch were relatively stable entities, tolerably safe against technological surprises. Today there is every reason to fear that even minor inventions and feints in the field of nuclear weapons can be decisive in less time than would be required to devise specific countermeasures. Soon existing nations will be as unstable in war as a nation the size of Manhattan Island would have been in a contest fought with the weapons of 1900. Such military instability has already found its political expression. Two superpowers, the US and USSR, represent such enormous destructive potentials as to afford little chance of a purely passive equilibrium. Other countries, including possible neutrals, are militarily defenseless in the ordinary sense. At best they will acquire destructive capabilities of their own, as Britain is now doing. Consequently, the concert of powers, or its equivalent international organization, rests on a basis much more fragile than ever before. The situation is further embroiled by the newly achieved political effectiveness of non-European nationalisms. These factors would normally, that is, in any recent century have led to war. Will they lead to war before 1980? Or soon thereafter? It would be presumptuous to try to answer such a question firmly. In any case, the present and the near future are both dangerous. While the immediate problem is to cope with the actual danger, it is also essential to envisage how the problem is going to evolve in the 1955-80 period, even assuming that all will go reasonably well for the moment. This does not mean belittling immediate problems of weaponry, of USU.S.S.R. tensions, of the evolution and revolutions of Asia. These first things must come first. But we must be ready for the follow-up, lest possible immediate successes prove futile. We must think beyond the present forms of problems to those of later decades. When reactors grow up, technological evolution is still accelerating. Technologies are always constructive and beneficial, directly or indirectly. Yet their consequences tend to increase instability, a point that will get closer attention after we have had a look at certain aspects of continuing technological evolution. First of all, there is a rapidly expanding supply of energy. It is generally agreed that even conventional, chemical fuel coal or oil will be available in increased quantity in the next 2 decades. Increasing demand tends to keep fuel prices high, yet improvements in methods of generation seem to bring the price of power down. There is little doubt that the most significant event affecting energy is the advent of nuclear power. Its only available controlled source today is the nuclear fission reactor. Reactor techniques appear to be approaching a condition in which they will be competitive with conventional, chemical, power sources within the US. However, because of generally higher fuel prices abroad, they could already be more than competitive in many important foreign areas. Yet reactor technology is but a decade and a half old, during most of which period effort has been directed primarily not toward power but toward plutonium production. Given a decade of really large-scale industrial effort, the economic characteristics of reactors will undoubtedly surpass those of the present by far. Moreover, it is not a law of nature that all controlled release of nuclear energy should be tied to fission reactions as it has been thus far. It is true that nuclear energy appears to be the primary source of practically all energy now visible in nature. Furthermore, it is not surprising that the first break into the intranuclear domain occurred at the unstable high end of the system of nuclei, that is, by fission. Yet fission is not nature's normal way of releasing nuclear energy. In the long run, systematic industrial exploitation of nuclear energy may shift reliance onto other and still more abundant modes. Again, reactors have been bound thus far to the traditional heat steam generator electricity cycle, just as automobiles were at first constructed to look like buggies. It is likely that we shall gradually develop procedures more naturally and effectively adjusted to the new source of energy, abandoning the conventional kinks and detours inherited from chemical fuel processes. Consequently, a few decades hence energy may be free just like the unmetered air with coal and oil used mainly as raw materials for organic chemical synthesis, to which, as experience has shown, their properties are best suited. Alchemy and automation. It is worth emphasizing that the main trend will be systematic exploration of nuclear reactions, that is, the transmutation of elements, or alchemy rather than chemistry. The main point in developing the industrial use of nuclear processes is to make them suitable for large-scale exploitation on the relatively small site that is the Earth or, rather, any plausible terrestrial industrial establishment. Nature has, of course, been operating nuclear processes all along, well and massively, but her natural sites for this industry are entire stars. There is reason to believe that the minimum space requirements for her way of operating are the minimum sizes of stars. Forced by the limitations of our real estate, we must in this respect do much better than nature. That this may not be impossible has been demonstrated in the somewhat extreme and unnatural instance of fission, that remarkable breakthrough of the past decade. What massive transmutation of elements will do to technology in general is hard to imagine, but the effects will be radical indeed. This can already be sensed in related fields. The general revolution clearly underway in the military sphere, and its already realized special aspect, the terrible possibilities of mass destruction, should not be viewed as typical of what the nuclear revolution stands for. Yet they may well be typical of how deeply that revolution will transform whatever it touches. And the revolution will probably touch most things technological. Also likely to evolve fast and quite apart from nuclear evolution is automation. Interesting analyses of recent developments in this field, and of near-future potentialities, have appeared in the last few years. Automatic control, of course, is as old as the Industrial Revolution, for the decisive new feature of Watt's steam engine was its automatic valve control, including speed control by a governor. In our century, however, small electric amplifying and switching devices put automation on an entirely new footing. This development began with the electromechanical, telephone, relay, continued and unfolded with the vacuum tube, and appears to accelerate with various solid-state devices, semiconductor crystals, ferromagnetic cores, etc. The last decade or two has also witnessed an increasing ability to control and discipline large numbers of such devices within one machine. Even in an airplane the number of vacuum tubes now approaches or exceeds 1,000. Other machines, containing up to 10,000 vacuum tubes, Up to 5 times more crystals, and possibly more than 100, cores, now operate faultlessly over long periods, performing many millions of regulated, pre-planned actions per second, with an expectation of only a few errors per day or week. Many such machines have been built to perform complicated scientific and engineering calculations and large-scale accounting and logistical surveys. There is no doubt that they will be used for elaborate industrial process control, logistical, economic, and other planning, and many other purposes heretofore lying entirely outside the compass of quantitative and automatic control and pre-planning. Thanks to simplified forms of automatic or semi-automatic control, the efficiency of some important branches of industry has increased considerably during recent decades. It is therefore to be expected that the considerably elaborated newer forms, now becoming increasingly available, will affect much more along these lines. Fundamentally, improvements in control are really improvements in communicating information within an organization or mechanism. The sum total of progress in this sphere is explosive. Improvements in communication in its direct, physical sense, transportation, while less dramatic, have been considerable and steady. If nuclear developments make energy unrestrictedly available, transportation developments are likely to accelerate even more. But even normal progress in sea, land, and air media is extremely important. Just such normal progress molded the world's economic development, producing the present global ideas in politics and economics. Controlled climate. Let us now consider a thoroughly abnormal industry and its potentialities, that is, an industry as yet without a place in any list of major activities, the control of weather or, to use a more ambitious but justified term, climate. One phase of this activity that has received a good deal of public attention is rainmaking. The present technique assumes extensive rain clouds, and forces precipitation by applying small amounts of chemical agents. While it is not easy to evaluate the significance of the efforts made thus far, the evidence seems to indicate that the aim is an attainable one. But weather control and climate control are really much broader than rainmaking. All major weather phenomena, as well as climate as such, are ultimately controlled by the solar energy that falls on the Earth. To modify the amount of solar energy is, of course, beyond human power. But what really matters is not the amount that hits the Earth, but the fraction retained by the Earth, since that reflected back into space is no more useful than if it had never arrived. Now, the amount absorbed by the solid Earth, the sea, or the atmosphere seems to be subject to delicate influences. True, none of these has so far been substantially controlled by human will, but there are strong indications of control possibilities. The carbon dioxide released into the atmosphere by industries' burning of coal and oil, more than half of it during the last generation, may have changed the atmosphere's composition sufficiently to account for a general warming of the world by about 1 degree Fahrenheit. The volcano Krakatoa erupted in 1883 and released an amount of energy by no means exorbitant. Had the dust of the eruption stayed in the stratosphere for 15 years, reflecting sunlight away from the Earth, it might have sufficed to lower the world's temperature by 6 degrees. In fact, it stayed for about 3 years. And 5 such eruptions would probably have achieved the result mentioned. This would have been a substantial cooling. The last ice age, when half of North America and all of northern and western Europe were under an ice cap like that of Greenland or Antarctica, was only 15 degrees colder than the present age. On the other hand, another 15 degrees of warming would probably melt the ice of Greenland and Antarctica and produce worldwide tropical to semi-tropical climate. Rather fantastic effects. Furthermore, it is known that the persistence of large ice fields is due to the fact that ice both reflects sunlight energy and radiates away terrestrial energy at an even higher rate than ordinary soil. Microscopic layers of colored matter spread on an icy surface, or in the atmosphere above one, could inhibit the reflection radiation process, melt the ice, and change the local climate. Measures that would affect such changes are technically possible, and the amount of investment required would be only of the order of magnitude that suffice to develop rail systems and other major industries. The main difficulty lies in predicting in detail the effects of any such drastic intervention. But our knowledge of the dynamics and the controlling processes in the atmosphere is rapidly approaching a level that would permit such prediction. Probably intervention in atmospheric and climatic matters will come in a few decades, and will unfold on a scale difficult to imagine at present. What could be done, of course, is no index to what should be done. To make a new ice age in order to annoy others, or a new tropical, interglacial age in order to please everybody, is not necessarily a rational program. In fact, to evaluate the ultimate consequences of either a general cooling or a general heating would be a complex matter. Changes would affect the level of the seas, and hence the habitability of the continental coastal shelves, the evaporation of the seas, and hence general precipitation and glaciation levels, and so on. What would be harmful and what beneficial, and to which regions of the Earth, is not immediately obvious. But there is little doubt that one could carry out analyses needed to predict results, intervene on any desired scale, and ultimately achieve rather fantastic effects. The climate of specific regions and levels of precipitation might be altered. For example, temporary disturbances including invasions of cold, polar air that constitute the typical winter of the middle latitudes, and tropical storms, hurricanes, might be corrected or at least depressed. There is no need to detail what such things would mean to agriculture or, indeed, to all phases of human, animal, and plant ecology. What power over our environment, over all nature, is implied? Such actions would be more directly and truly worldwide than recent or, presumably, future wars, or than the economy at any time. Extensive human intervention would deeply affect the atmosphere's general circulation, which depends on the Earth's rotation and intensive solar heating of the tropics. Measures in the Arctic may control the weather in temperate regions, or measures in one temperate region critically affect another, one quarter around the globe. All this will merge each nation's affairs with those of every other, more thoroughly than the threat of a nuclear or any other war may already have done. The indifferent controls. Such developments as free energy, greater automation, improved communications, partial or total climate control have common traits deserving special mention. First, though all are intrinsically useful, they can lend themselves to destruction. Even the most formidable tools of nuclear destruction are only extreme members of a genus that includes useful methods of energy release or element transmutation. The most constructive schemes for climate control would have to be based on insights and techniques that would also lend themselves to forms of climatic warfare as yet unimagined. Technology like science is neutral all through, providing only means of control applicable to any purpose, indifferent to all. Second, there is in most of these developments a trend toward affecting the Earth as a whole, or to be more exact, toward producing effects that can be projected from any one to any other point on the Earth. There is an intrinsic conflict with geography, and institutions based thereon, as understood today. Of course, any technology interacts with geography, and each imposes its own geographical rules and modalities. The technology that is now developing and that will dominate the next decade seems to be in total conflict with traditional and, in the main, momentarily still valid, geographical and political units and concepts. This is the maturing crisis of technology. What kind of action does this situation call for? Whatever one feels inclined to do, one decisive trait must be considered. The very techniques that create the dangers and the instabilities are in themselves useful, or closely related to the useful. In fact, the more useful they could be, the more unstabilizing their effects can also be. It is not a particular perverse destructiveness of one particular invention that creates danger. Technological power, technological efficiency as such, is an ambivalent achievement. Its danger is intrinsic. Science the indivisible. In looking for a solution, it is well to exclude one pseudo-solution at the start. The crisis will not be resolved by inhibiting this or that apparently particularly obnoxious form of technology. For one thing, the parts of technology, as well as of the underlying sciences, are so intertwined that in the long run nothing less than a total elimination of all technological progress would suffice for inhibition. Also, on a more pedestrian and immediate basis, useful and harmful techniques lie everywhere so close together that it is never possible to separate the lions from the lambs. This is known to all who have so laboriously tried to separate secret, classified science or technology, military, from the open kind. Success is never more nor intended to be more than transient, lasting perhaps half a decade. Similarly, a separation into useful and harmful subjects in any technological sphere would probably diffuse into nothing in a decade. Moreover, in this case successful separation would have to be enduring, unlike the case of military classification, in which even a few years' gain may be important. Also, the proximity of useful techniques to harmful ones and the possibility of putting the harmful ones to military use, puts a competitive premium on infringement. Hence the banning of particular technologies would have to be enforced on a worldwide basis. But the only authority that could do this effectively would have to be of such scope and perfection as to signal the resolution of international problems rather than the discovery of a means to resolve them. Finally and, I believe, most importantly, prohibition of technology, invention and development, which are hardly separable from underlying scientific inquiry, is contrary to the whole ethos of the industrial age. It is irreconcilable with a major mode of intellectuality as our age understands it. It is hard to imagine such a restraint successfully imposed in our civilization. Only if those disasters that we fear had already occurred, only if humanity were already completely disillusioned about technological civilization, could such a step be taken. But not even the disasters of recent wars have produced that degree of disillusionment, as is proved by the phenomenal resiliency with which the industrial way of life recovered even or particularly in the worst-hit areas. The technological system retains enormous vitality, probably more than ever before, and the counsel of restraint is unlikely to be heeded. Survival a possibility. A much more satisfactory solution than technological prohibition would be eliminating war as a means of national policy. The desire to do this is as old as any part of the ethical system by which we profess to be governed. The intensity of the sentiment fluctuates, increasing greatly after major wars. How strong is it now, and is it on the up or the downgrade? It is certainly strong, for practical as well as for emotional reasons, all quite obvious. At least in individuals, it seems worldwide, transcending differences of political systems. Yet in evaluating its durability and effectiveness, a certain caution is justified. One can hardly quarrel with the practical arguments against war, but the emotional factors are probably less stable. Memories of the 1939-45 war are fresh, but it is not easy to estimate what will happen to popular sentiment as they recede. The revulsion that followed 1914-18 did not stand up 20 years later under the strain of a serious political crisis. The elements of a future international conflict are clearly present today and even more explicit than after 1914-18. Whether the practical considerations, without the emotional counterpart, will suffice to restrain the human species is dubious, since the past record is so spotty. True, practical reasons are stronger than ever before, since war could be vastly more destructive than formerly. But that very appearance has been observed several times in the past without being decisive. True, this time the danger of destruction seems to be real rather than apparent, but there is no guarantee that a real danger can control human actions better than a convincing appearance of danger. What safeguard remains? Apparently only day-to-day, or perhaps year-to-year, opportunistic measures, a long sequence of small, correct decisions. And this is not surprising. After all, the crisis is due to the rapidity of progress, to the probable further acceleration thereof, and to the reaching of certain critical relationships. Specifically, the effects that we are now beginning to produce are of the same order of magnitude as that of the great globe itself. Indeed, they affect the Earth as an entity. Hence further acceleration can no longer be absorbed as in the past by an extension of the area of operations. Under present conditions it is unreasonable to expect a novel cure-all. For progress there is no cure. Any attempt to find automatically safe channels for the present explosive variety of progress must lead to frustration. The only safety possible is relative, and it lies in an intelligent exercise of day-to-day judgment. Awful and more awful. The problems created by the combination of the presently possible forms of nuclear warfare and the rather unusually unstable international situation are formidable and not to be solved easily. Those of the next decades are likely to be similarly vexing, only more so. The USU.S.S.R. Tension is bad, but when other nations begin to make felt their full offensive potential weight, things will not become simpler. Present awful possibilities of nuclear warfare may give way to others even more awful. After global climate control becomes possible, perhaps all our present involvements will seem simple. We should not deceive ourselves. Once such possibilities become actual, they will be exploited. It will, therefore, be necessary to develop suitable new political forms and procedures. All experience shows that even smaller technological changes than those now in the cards profoundly transform political and social relationships. Experience also shows that these transformations are not a priori predictable and that most contemporary first guesses concerning them are wrong. For all these reasons, one should take neither present difficulties nor presently proposed reforms too seriously. The one solid fact is that the difficulties are due to an evolution that, while useful and constructive, is also dangerous. Can we produce the required adjustments with the necessary speed? The most hopeful answer is that the human species has been subjected to similar tests before and seems to have a congenital ability to come through, after varying amounts of trouble. To ask in advance for a complete recipe would be unreasonable. We can specify only the human qualities required: patience, flexibility, intelligence.